So in this video we will be looking at units and why they're important. So to this point I'm going to start by having you just think for a moment about what is the point of having units at all? Why do we have meters or feet or arshins, for instance? What is the point of that? What purpose do they serve? So pause about that for a moment and then we'll get back. Okay. So hopefully the idea that you came up with is that they exist to facilitate communication. And how do they do that? They do that by being able to reference something that's agreed upon. So it doesn't particularly matter what it is you reference, as long as everyone knows what it is you're referencing. An example of this would be if I say that the weather outside is 20 degrees, presumably you say, oh, hey, it's a pretty decent day. Probably don't need a heavy coat. Oh, wait, do you think that you're freezing? So you see, that's the thing, is we have to agree on something. When I said it was 20 out, of course I was thinking those 20 degrees Celsius, because after all, there's only a couple of countries on Earth that don't use Celsius for temperature in common use, so I was just kind of playing the odds there. But if you're from the United States, for instance, you would probably be mentally referencing Fahrenheit, and then you'd be thinking, that winter coat is sounding pretty good. And you can argue back and forth what may or may not be a better choice to do, but the whole point is that as long as we know what it is we're referencing, when someone tells us that's 20 out, we know how to dress. And so ultimately, that's the point of units, is just we all get together and we agree on something in order to go forward. Now, the main system that pretty much every unit system, including what's used in the United States, is ultimately based on, more on standard American equivalents in a bit, are what's called Système International, and my apologies for butchering the French. Système, S-Y-S-T-E-M-E, International. What we usually call SI for short, units. Now, it's sort of an important news bulletin. At the time of the recording of this video in first half of 2020, there really aren't any books out there that are up to date, intro physics books out there that are up to date on the current definition of the SI units. There was a major overhaul of the definitions that was adopted on May 20th of 2019. So I will be taking a bit of time to go over what the new definitions are and how they contrast to the old definitions that you may have been aware of from previous instruction in other courses. In a certain sense, the philosophy of the definitions has looped full circle. In the very original conception of the metric system. The idea was that the Earth itself would define the units. So for instance, the meter ideally was supposed to be a certain fraction of the distance between the equator and the North Pole. The gram, or later the kilogram, were supposed to be based on the properties of water and the definition of the meter. The second gets defined based on the rotation of the Earth. As things went along, though, we had problems with all of these things. For instance, with the meter, it would be unwieldy to commission an international survey every time you wanted to cut a piece of wood. So you need to make meter sticks. And to do that, it'd be nice if you had a prototype meter. So there was a series of surveys that were commissioned, 3 of them. The people felt that the third of the surveys, figuring out the distance between the equator and the North Pole, was the best. Turned out the second one was the best, but they went with the third one, and so the definition of the meter doesn't quite work out with that ideal. Using water to define things like mass and temperature seemed like a really, really good idea. The problem is that from a chemical point of view, water is about as close to a universal solvent as you're going to find. All sorts of things love to dissolve into water. And it turns out that those impurities create all sorts of technical issues with it. And so ultimately, people just did their very best to make an appropriate blob of water and then replaced that ultimately with a blob of metal that they said was a kilogram. That was stored in a vault in France and was actually what we meant by a kilogram until May 20th of 2019. So it was a great idea. Even the second had problems. It turns out that because of interactions with the moon, the Earth's rotation rate slows down. So they had to start doing things like saying, well, we mean a second, as a certain fraction of the Earth's rotation on a certain date. As time elapsed, that got harder and harder and harder to do. Eventually that got decoupled and referenced to atomic clocks. So it was all a really good idea, a noble idea of let nature define the units and then we just reference off of it. But the technical challenges made that not feasible. We're in a different place now, and it turns out that instead of saying let the Earth define the units, the new approach is to say let nature define the units. So the metric system the SI unit system is now based on defining 7 physical constants to be exact numbers. And that defines the meter or the kilogram or the second, etc. And it no longer makes reference to a particular type of experiment. For instance, you heard me talk about an atomic clock. The previous definition of the second involved such a device. Now you can build any device you want, although to do the job, because the second has been defined through a choice of units, or through a choice of physical constants. However, the International Bureau of Weights and Measures will still be publishing guides of what they consider to be official best practices. So for the time being, the second, let's start there, is still going to be measured by an atomic clock, but the direction of the definition has changed. So the unit is the second, the symbol is a lowercase s. In the old definition, you would have used a cesium-133 atomic clock. The isotope cesium-133 can be coaxed into emitting light in what's called a hyperfine transition. What that is need not concern us here. And the idea was that you could count the crests of light from this hyperfine transition going past you. And after 9,192,631,770 of those crests of light waves went by you, you said that that was a second. The new definition has flipped this. So in the new definition, this is probably the second hankiest of the constants that got defined. Delta nu sub cesium. This is, we now say that by definition, the frequency of light emitted from that hyperfine transition in cesium that I was talking about is 9,192,631,770 hertz. And hertz is just a way of writing 1/seconds. So this has flipped the direction of the definition. So in the old definition, the second was defined as so many waves of this light go past. In this new definition, what we do is we say that this frequency of light that gets emitted is this exact frequency. And now you are free to use any technology that you would want. For instance, if you were to feel that you could make a better clock using rubidium atoms, that would be fine. You would still calibrate it off of this cesium frequency, but you could make a clock using rubidium atoms instead, or whatever technology you want in the future. The second is now defined as being is defined as being implicitly through this frequency. Okay, so that's our unit of time. The unit of length in the system is the meter, and its symbol is m. And again, lowercase. So this one's probably had the most storied history. You heard me reference that was based on the distance between originally based on the distance between the equator and the North Pole. Eventually people figured out that the Earth wasn't rotationally symmetric enough for that to be a reliable definition just in and of itself. So then that got to be modified to say there's a certain fraction of the distance between the equator and the North Pole going through Paris. And then it was the length of a rod that was based on that erroneous third survey that got mentioned. And the problem with having a rod as your reference for length, one, it expands and contracts, so you have to be very careful about its temperature when you are calibrating things off against it. And two, this rod is an example of what's called an artifact standard. That means that we're saying the definition of the meter was the length of that exact rod that was kept in a vault in France. Well, what if someone drops the rod? Then literally you don't have a meter anymore. Keep that thought in the back of your mind when we get to mass. It didn't get dropped, but anyway, with time, lasers got developed, and people realized that they could actually measure the length of this rod using a Krypton 86 laser, and they could say that they measured its length to be a certain exact number of wavelengths of light from this laser. And then people started looking and saying, you know what? Atomic clocks are about 1,000 times more accurate than these lasers. So we will go ahead and define the meter by saying it's the distance that light travels in a certain fraction of a second, thus implicitly defining the speed of light. The current definition now flips that on its head. In the current in the current definition, we say that the speed of light, its symbol is c, is exactly 299,792,458 meters per second. And again, this is an exact quantity. So the second has already been defined by means of defining the constant for the frequency of light being emitted from a hyperfine transition in cesium. So since the second has already been defined, basically what we've done is we have now tied our definition of length, the meter, to the definition of the second through the inherent physical property of the speed of light. So the best practice is to do what's called a time of flight measurement, where you set up a couple of cells at either end of the thing that you want to measure, and you measure the amount of time it takes for light to travel from one detector cell to the other detector cell. And from that, you can figure out how many meters the light traveled. So that is in practice how we make a meter. And then from there, you can go and make meter sticks. This is an example of a lab reproducible definition. If you've got suitable scientific equipment lying around, you can go and make just as good a meter, or just as good a second for that matter, as anybody else. You don't have to reference any particular object. In fact, these constants are things that would be known to pretty much any civilization that has decent science. So if we were ever to make contact with some other civilization outside our solar system, with us just exchanging what our values for these constants are, they would be able to reconstruct all of our units. Okay, on to mass. This one was probably the biggest mess. The unit for mass is the kilogram. Now, if you've had some chemistry, they have told you that the unit of mass there is the gram. And historically, that was supposed to be the idea. It was supposed to be the mass of 1 cubic centimeter of water. But like I mentioned earlier, water dissolves all kinds of stuff. So it turned out to not work out very well. The best attempts to make the most pure water possible, they eventually realized they had to have at least a liter of water lying around to do anything any good. So that's a cube 10 centimeters on a side, or 1,000 cubic centimeters, so that would be a mass of a kilogram. So what we do is, for purposes of the prefixes, like the kilo or the mega prefix or whatever, you pretend that the gram is the unit for the purpose of the prefix, but the base unit is actually the kilogram. And there was an object made. It was a blob of platinum iridium alloy metal that was kept in a vault in France, that, to the best of everyone's ability, balanced off on a scale as closely as it possibly could to a liter of pure water. Now, this object did not come out of the vault very often. One of the problems with artifact standards is you don't want to, on one hand, you don't want to handle them, because anytime you handle them, you could somehow cause damage to them. But on the other hand, if you don't pull them out of the vault at least occasionally, national governments won't be able to see if their copies have drifted or not. So the kilogram got pulled out of the vault about every 20 to 30 years. And the previous time it got pulled out of the vault, when it was compared off against all of the national copies, what was noticed was that the base, roughly the mass of the national copies, had all changed and in the same direction. Now, the plausible conclusion from that would be that the mass of the kilogram changed, possibly due to improper handling the time before that it was pulled out, a couple decades earlier. But there's literally no way to know. And since by definition the kilogram is the mass of that blob of metal, everything changed. Not by much, not enough that it matters to anybody for just about anything, but it changed. And it turned out that trying to come up with a lab reproducible definition for mass was incredibly hard. Did I just write mass twice? My apologies there. Kilogram. And so, because of this issue, national governments stepped up their efforts to develop lab reproducible definitions for the kilogram, and we succeeded. So the current definition of the kilogram is based on a constant in quantum mechanics, which you'll run into in the next course, called the Planck Constant. It is now set to be exactly 6.6260715 times 10 to the negative 34 joule seconds. A joule is a Newton times a meter, and a Newton is a kilogram times a meter divided by seconds squared. So at the end of all of this, what you have is a kilogram meters squared per second is what you get if you take a joule second, break it all the way down to base units. But the meter and the second have already been defined by the second via that constant for the frequency of light coming out of cesium. The meter has been defined through the setting the speed of light to that exact value. So Planck's constant is now also an exact value. And this now defines the kilogram. So it turns out that there's going to be in practice, there's going to be a two-prong approach onto this. So in order to make all of this work, the best practice is to use a device called a Kibble balance, or it's also known as a Watt balance. Or what you can do is compare effectively you're putting a known magnetic force in one quote-unquote pan of the balance, and you put the object in the other and measure the gravitational force of the Earth on it against this known magnetic force. It's very fussy. There's one of these currently at the National Institutes of Standards and Technology in Gaithersburg, Maryland. There'll probably be a couple more that national governments will build. These things are incredibly fussy beasts, and it'll probably be quite a while before, say, a company like O-House will have one of these around. But what you can do is you can take whatever you want to use for mass calibration. You can take it to NIST, and they can weigh it in their Kibble balance. And so then you'll know exactly what you have for calibration purposes. So the platinum iridium cylinders that everybody's been using will slowly get phased out. And what's going to replace them, at least in the intermediate term, is these spheres of very pure silicon. And to do that, the amount of a substance also had to be defined. So the unit for this is the mole, M-O-L-E, symbol M-O-L. And this is done by making Avogadro's number also exact. It is now, by definition, exactly 6.022140765. Please don't commit these numbers to memory. Times 10 to the 23rd inverse moles. And the inverse mole there is just to make units work out. So when we say that we have a mole of anything, it could be a mole of bricks. It means that we have 6.022140765 times 10 to the 23rd of them. Exactly. All the rest of the digits are zeros. With this definition, the mole locked in, this allows chemists to do something very clever where they can make rather sizable isotopically pure spheres of silicon that are pretty darn close to a kilogram. These spheres can then be weighed in a Kibble balance so you can figure out exactly what they are. And then those spheres can be used for calibration when, say, a company like O-House comes in every so often to check their standards. Okay. So for the last few here, the temperature. The unit temperature is the Kelvin. And the symbol is a K. We'll run into this later, and we'll do a more detailed treatment of it at that time. But it's based on setting a number called Boltzmann's constant to an exact value. It's 1.380649 times 10 to the negative 23rd joules per Kelvin, and this is now exact. In the next course, you'll run into electric current and electric charge. for historic reasons, electric current is the base quantity in this system. The unit is the ampere, symbol capital A. And it's now what we've done is we have set the fundamental quantum of electric charge. So the charge on the electron is the negative of this to be 1.602176634 times 10 to the negative 19 coulombs. And again, that's an exact number. And a coulomb is an ampere times a second. The definition for back compatibility. So really, charge is the base unit, which is what it should be, as you'll see in the next course. But in order to maintain historic compatibility with the older definitions that had to deal with some practical issues, the definition is rather, the exact word in the definition is rather tortured in order to keep the ampere as the base unit and the coulomb as the derived unit, we call it, what you get when you multiply base units together to get something else. But conceptually, it's the other way around. And then what we will not cover in this course or the next one, but I'll throw it in for completeness sake, is luminous intensity. If you're Nikon, you care. If you're and if you're buying light bulbs, you care. And for pretty much anything else, you don't really care. The unit is the candela. And so the lumen gets derived off of this. The unit is CD. Just for absolute completeness sake, this is again another one of these torturously hard to motivate units or constants. It's just they created a constant that they called the candela constant and set it equal to 683 candela per steradian watt. A steradian is a measure of the 3D equivalent of angle, and a watt is power over time. So anyway, that is the current SI unit system. So we've retired the definitions that at the time of recording this video you are likely to be finding still in textbooks, and these are the new current official ones. And unless there's some major discovery, like maybe we discover that some of these constants are somehow not so constant or something like that, barring anything really huge, hopefully we're done. Almost all these units have been redefined multiple times around different experiments as technologies got better and better and better. But by setting all these constants to be these exact numbers, the units have now been defined in terms of fundamental properties of nature. And these are definitions that are agnostic to the exact, or indifferent to the exact technology used to measure them. Okay. So I did promise, I mentioned that in the United States, our unit system is actually derived from metric, and that is correct. Believe it or not, we were the 13th signatory of the International Treaty of the Meter. But instead of doing a full-blown conversion to metric, what the United States did is it redefined its commercial units in terms of the corresponding metric units. I won't go through the whole list of them here, but by law in the United States, and this is not the same for the UK, although the UK is now a fully metric country, a foot by law in the United States is exactly 0.3048 meters. Again, that number is exact. So the traditional unit of length of the foot is just referencing bundles of 30.48 centimeters, or 0.3048 meters. Okay, and the other units are all defined in similar ways. Okay, should probably spend just a quick bit of time working just a couple fast examples on unit conversions, but we'll go ahead and do that in the next video.